Welcome to the Unit 2 review. Here's number 1, Part A. If p of x equals 4x to the third minus 5x minus 2, let's use synthetic substitution to solve p of 2. Okay, synthetic substitution. Well, 2 will be my divisor, and that's going to go in the box right there. And now, my coefficients of my dividend would be the cubic is a 4. And I'm going to do a shotgun method here. The quadratic, do you notice there's no quadratic term, so the quadratic is a 0. The linear is a -5, and the constant is -2. All right, let's go ahead and bring our 4 down. And then shotgun method, we're going to go 2 steps in 1, so 4 times 2 is 8, plus 0 is 8. 8 times 2 is 16, minus 5 is 11. 11 times 2 is 22, minus 2 would be a 20, so that tells me that p of 2 equals 20. Okay, now for part B, our divisor is going to be -0.5, so let's put that in the box. All right, and then shotgun method again, let's bring down our 4. 4 times -1/2 would be -2 plus 0 is -2. -2 times -1/2 would be +1 minus 5 is a -4. And -4 times -1/2 would be a 2 minus a 2, and I get a 0. So -0.5 is a root of this quadratic or the cubic up here. So I'm going to say that p of -0.5 is 0. All right, part C, one more. Oh, look at our divisor this time, I. Okay, so now let's bring down the 4. Now be careful, we're going to get some complex numbers here. 4 times I is 4i plus 0 is still 4i. And then 4 times I would be 4i squared, or -4, minus 5 is a -9. And then -9 times I is -9i, but I've got to add that to the -2, and I want my answer in a plus bi form. So the real part would be the -2. I'll bring that down. And then what was my imaginary part again? -9 times I minus 9i. So that tells me that p of I equals -2 minus 9i. Number 2. If 2 is a 0 of p of x equals 3x squared plus kx minus 8, find the value of k. Okay, well, let's break this down and do a little synthetic substitution again. The 2 is a 0, so that I'm going to divide by 2 using synthetic substitution. So let's put 2 in the box. All right, and then I need to write my coefficients of p of x, and we're going to do that using the shotgun method. So let's go ahead. The quadratic would be a 3. The linear would be a k. That's interesting. And the constant would be -8. Okay, shotgun method. Let's bring down the 3. 3 times 2 is 6 plus k, 6 plus k. And then 6 plus k times 2 would be 12 plus 2k. But don't forget, I have to subtract that 8 right there. So what is 12 plus 2k minus 8? Well, let's combine our like terms, and that would be 4 plus 2k. Now, they told me at the beginning of this problem that 2 would have to be a 0. So doesn't that mean that this 4 plus 2k would have to equal 0? So if I take the equation 4 plus 2k equals 0, and they're asking me to find a value for k, I'm just going to take this and solve for k. So I'd say, well, it looks to me like this k would have to be a -2. And if you need to show every step, go ahead. But I'm just going to go 4 plus 2 times -2 is 4 minus 4, and that equals 0. So k equals -2. Okay, number 3. When a polynomial p of x is divided by x plus 3, the quotient is x squared minus x plus 5, and the remainder is 2. Let's find p of x. Well, if we remember our quotient remainder theorem, because all we're doing is we're talking about dividing p of x by a linear polynomial. So we're dividing polynomials. Quotient remainder theorem. It's just your definition of elementary division. A dividend will always equal a divisor times a quotient plus a remainder. Now, let's show that with elementary numbers. Let's take 10 divided by 3. All right, by the quotient remainder theorem, the dividend would have to equal the divisor times the quotient plus the remainder. Excuse me. So let's set that up. Do you know the parts? 10 is the dividend, so 10 equals, and 3 is my divisor. So 10 equals 3 times my quotient. How many times does 3 go into 10? 3 times. 3 times 3 plus the remainder. Well, what's the remainder when 10 is divided by 3? That would be a 1. Now, do you guys agree that 10 equals 3 times 3 plus 1? So now, let's do this with polynomials. Okay, so p of x is being divided. So p of x is my dividend. P of x equals, and what is p of x being divided by? Because that would be my divisor, x plus 3, times, now what's the quotient? Look, they gave it to me. X squared minus x plus 5 plus the remainder. If I knew the remainder, I'd be done. Oh, look at this, and the remainder is 2. So guess what? P of x equals x plus 3 times the quantity x squared minus x plus 5 plus 2. And I want this left in this form because I want to clearly see the divisor times the quotient plus the remainder. Thank you. Okay, number 4. 2 roots of the equation x to the 4th minus 3x to the 3rd minus 14x squared plus 12x plus 40 equals 0 are, wow, that's a big old quartic equation. That's a mouthful. But the 2 roots are x equals 2 and x equals 5. Find the remaining roots. Well, we have a quartic which will have 4 roots, and they've given us 2 of them. So we only have 2 more to find. So let's do synthetic substitution to see if we can find those remaining 2 roots. All right, so the first root they gave me is a 2, so I'm going to do synthetic substitution with a 2 in the box. And then I'm going to write my coefficients of my polynomial equation up here. All right, and I'm going to use the shotgun method. So the quartic coefficient is a 1. The cubic coefficient is a -3. The quadratic is a -14. The linear is a 12. And the constant is 40. Okay, shotgun method. Let's bring down the 1. Oh, and remember, this has to be a 0, so I put the 0 there already. Right on. Okay, so let's bring down the 1. And 2 times 1 is 2 minus 3, -1. -1 times 2 is -2 minus 14, -16. -16 times 2, -32 plus 12, -20. And look at this, -20 times 2 is -40 plus 40, and there's my 0. Now, the other given root is x equals 5. Let's put a 5 in the box and use our coefficients of our quotient polynomial right here. And this is a trinomial. This is a cubic polynomial. All right, and I know again I better get a 0, so I'll put that right there. Now let's bring down the 1, and 1 times 5 is 5, minus 1 is 4. 4 times 5 is 20, minus 16 is 4 again, and 4 times 5 is 20, minus 20, and there's my 0. Now look at these coefficients right here of this quotient polynomial. This is a quadratic. So let's write down our quadratic. We have 1x squared. We have 4x's plus 4. And let's hope this is factorable right here because we need the zeros of this quadratic now. And isn't that a perfect square trinomial? It looks like it to me, but let's double check. So x squared would be an x times an x. and I need a product of 4 and a sum of 4. So isn't that just a plus 2 plus 2? So I have a factor of x plus 2. That gives me a root of negative 2. And because I have two factors of x plus 2, this negative 2 is a double root. It counts for 2 roots, and those are my 2 remaining roots right there. Number 5. Let's sketch x times x plus 1 times x minus 2 quantity squared. And remember, this is just a rough sketch. We're visualizing this. We have graphing calculators. We can get the perfect graph, but we need to be able to get a rough sketch of a polynomial that we can factor. Okay, so let's draw a coordinate plane, nothing fancy, and let's look at our factors to get our roots. The first factor is x. That gives me a root of 0. The second factor is x plus 1. And that's going to give me a root of negative 1. The third factor is x minus 2, so that's going to give me a root of 2. And because that factor x minus 2 is being squared, that's a double root. All right, now, what is this? This is a quartic. So we have a quartic whose leading coefficient is, well, if we expanded this, wouldn't my leading term be x to the 4th power? So my leading coefficient is a 1, which is a positive number. That means a quartic whose leading coefficient is positive. Well, all quartics work horizontally, either 2 to 1 or 3 to 4. So this one is going to be, because the leading coefficient is positive, it's got to work from quadrant 2 over here and finish up in quadrant 1 right here. So let's start in quadrant 2 and go through our single root. And then we take a turn and go through our second single root at the origin. And then we take another turn and we work down towards our double root. And remember the shape of a double root now. All right, we're going to come down and just kiss the x-axis. And then work back up, finishing in quadrant 1 like we said we would. And that's the shape of a double root. This polynomial is tangent to the x-axis at x equals 2. And that's an almost perfect sketch of y equals x times the quantity x plus 1 times the quantity x minus 2 squared. We're not going to worry about our extrema, this valley, that peak. Well, we know that valley right there. In calculus, we will find exact answers to those as well. Or we could use technology to find them right now. Great sketch. Okay, number 6. Give an equation of the cubic graph shown. So now we're going the other way. We just started with a polynomial in factored form, and they ask you to sketch. Now they're giving you the graph with some very detailed information, by the way, and they're asking for the equation. So let's start y equals, all right, well, what's this look like to you? I think this might be a cubic. What do you think? And let's start with our roots to get factors. So the first root I see is a negative 2, and that's going to give me a factor of x plus 2. The next root I see is positive 1, and that's going to give me then a factor of x minus 1. And the third root I see is 1, 2, and 3. All right, so that's going to give me a factor of x minus 3. All right, and do you notice that they discretely gave you another point on this graph? If I have a point on the graph that is not a root, I can get a scalar multiple of this general cubic right here. Look at this point right here. And this doesn't have to be a y-intercept. It could be anywhere on the curve other than a root. But what's the coordinates of that point? Well, x is 0 and y is 1, 2, 3. Okay, good. Now that means I can put a scalar factor of a right there, and I have enough information to solve for this a to give the perfect equation to this cubic right here. So 0, 3 implies, well, my y is going to be a 3. And then I have equal to a times, and all of these x's are 0, so I have a 2 times -1 times -3. Now let's solve for that a right now. So a equals, well, that would be 6a equals 3. So a would be 3 over 6, which I'm going to write as 1/2. Now I'm ready to answer this question. So y equals a, which is 1/2, quantity x plus 2 times the quantity x minus 1 times the quantity x minus 3. Great problems. Okay, number 7. Ooh, this is a great looking story problem right here. A rectangular enclosure. Well, all great story problems start with a great diagram, so I am going to draw a what? A rectangle. Is to be made using a barn as one side. So I'm going to have a barn on one side of this rectangular enclosure. There it is right there. And I have 80 meters of fencing to form the other 3 sides. So these 3 sides, I have 80 meters of fencing. Why don't we just put that 80 right there? Now, this is a rectangle, and I don't know what this dimension is, but I know it's congruent to this other side over here. So I'm just going to call both of these x and x. Now, I had 80 meters of fencing for all 3 sides, but I've used 2 x's up, so that means this dimension would have to be 80 minus those 2 x's. Oh, how cool. Now let's find the area of the rectangle. Well, our area of a rectangle is just going to be length times width. So how about we go x times -2x for our -2x squared. I'm putting this in general form. And then x times the 80 to get plus 80 x's. And there is the area formula. A of x equals -2x squared plus 80x. Now, if I was just looking at this function, this area function right here, all right, I'd be thinking it's defined for all real numbers because a quadratic would be defined for all real numbers. But this is real world. That means I have a real world domain. I cannot put any x into this problem and have the problem make sense. I can put a lot of them in there, but not any. So here's what I need to do. All right, x has to be in an interval. So I'm going to write a double inequality. And then I look at my dimension that represents x over here. Would you all agree that x would have to be bigger than 0 to create a rectangle? So let's go 0 is less than x. And now, what number does x have to be less than? Well, I had 80 meters of fencing. And if I used 40 here and 40 on the other side, I would lose this dimension right here. So that means x has to be less than 40, and that is my real domain right there. All right, well, let's find our maximum area. Okay, so, and look at that. My leading coefficient is -2, so I have a quadratic that's going to open downwards. All right, that means the extrema, or the maximum, will occur on the vertex, and the vertex is on the axis. The equation of an axis is always x equals -b over 2a. So the axis in this situation would be x equals, and what's the opposite of my b? -80 over 2 times a. 2 times -2 is -4, and -80 divided by -4 is 20. So the maximum area will occur when x equals 20 meters. So let's find a of that 20. Now I could plug 20 into my general form of my quadratic right here. But I think it might be easier to just put it in as an x. That would be 20. And this would be 80 minus 40. This would be 40. 40 times 20 is 800. 800. And remember, my units are in meters, so my area would be square meters. So with these constraints, we can create a rectangle that has an area of 800 square meters. That's a pretty big rectangular enclosure. Number 8, part A. If p of x equals 2x to the fourth minus 3x to the third minus 1, explain how you know p of x equals 0 has at least one real root between x equals 1 and x equals 2. Well, just looking at this right now, I really don't know that. I do know that this is a quartic, so it could have 0 roots and up to 4 roots, but how can I tell if there's a root between 1 and 2? Well, let's think a second. Isn't any polynomial continuous? And so we could use the location principle, all right? And what the location principle means is this. If a polynomial is continuous, which they all are, and now what if p of 1 and p of 2 have opposite signs? So what is p of 1? Well, if x is 1, I get a 2 minus 3 is negative 1. Minus 1, I get a negative 2. Now I'm hoping p of 2 then is positive. 2 to the fourth would be 16 times 2, 32. Minus 24, 32 minus 24, that'd be an 8. Minus 1 more, and that's a 7. And hallelujah, p of 1 is negative and p of 2 is positive. And because p of x is a polynomial, meaning it is continuous, that graph would have to cross the x-axis somewhere between x equals 1 and x equals 2. So let's just write that down. Implies p must have a root in the open interval between 1 and 2. So there's part A. Now part B, find each real root of p of x equals 0 to the nearest tenth. Now they're giving you some serious hints right now that this probably is not going to be factorable. I'm betting there are no rational roots because they've told us to find real roots and to round. That tells me they want me to break out my calculator. So I'm going to get my calculator out and I want to visualize what the graph would look like beforehand. Okay, so here it is, but let's visualize. Zoom standard, 2x to the fourth now. Shouldn't I expect, if I see everything I need to see, a graph that's going to start in quadrant 2 and finish in quadrant 1 is going to work horizontally? Let's see if I can see that with my standard window. There it is right there. Now I need to use my calculator to find this root and that root. So this quartic equation is going to have 2 roots. Okay, right on. Okay, well, you all know how to do that. So let's go second calc and choose 2 to find the 0. And then it's going to ask you for a left bound, arrow left of it, and then a right bound, arrow to the right, and then guess, just hit enter one more time. And the first root I got, and these are approximations, these are not exact, but my calculator gave me x equals approximately negative 0.6. And then I'm going to do that again for the second root. And here it is right here. And again, I did left bound, so I arrowed to the left of that root and I hit enter. Then I arrowed to the right of that root and I hit enter. And then I hit guess, enter one more time. And my calculator gave me the 1.6 right there. So there it is. Okay, number 9. Solve 2x to the third minus 3x squared equals 6x minus 9. So remember when we did our various methods of solving polynomial equations. Well, before we begin to determine the method, we better put this in general form. So I'm going to do the general form of a cubic equation. This is cubic, which means I'm just going to get everything on one side. So on the right, I'm going to leave my 0. And on the left, I would have 2x to the third power minus 3x squared. And then we're going to have to subtract the 6x's minus 6x. And then we're going to have to add 9. So here is my cubic with 4 terms. And this is in general form right there. Now, do you remember the method that we can try whenever we have a cubic with 4 terms? That's right, grouping. Let's see if we can group this and get it into factored form. So that means I'm going to take the first two terms, the cubic and the quadratic, and group them. Are they factorable? Oh, yeah. I see a common factor of x squared, so I'll factor the x squared out and go x squared times what is 2x to the third. That'd be a 2x. X squared times what is negative 3x squared minus 3. Now I group the next two terms, the linear and the constant, and I am hoping that when I do that, I'm going to have a factor of 2x minus 3. So I always start with that factor of 2x minus 3. And then I just think to myself, I need a negative 6x. Well, distributive property, negative 3 times 2x would be negative 6x. So there's my negative 3. And let's make sure this works. So one more time, negative 3 times 2x is negative 6x. And negative 3 times negative 3 is positive 9. So that works, equals 0. And now let's write down our factors. So do you see the common factor, the binomial 2x minus 3? I'll put that right there. And what did I multiply that 2x minus 3 by first up here? X squared. And then I multiplied it by negative 3. So there's my factors right there. All right. Now, by the zero product property of algebra, one of these two factors would have to equal 0. So that means x squared minus 3 equals 0, or x squared equals 3. And if x squared equals 3, then square root both sides, and x will equal, don't forget your plus or minus root 3. All right, and there's my two irrational conjugates, and I only have one more root because this is a cubic equation. So 2x minus 3, if I set that equal to 0, I get 2x equals 3, so x equals 3 halves. And there are my three roots. A rational root and then two irrational conjugates right there. Number 10, solve 3x to the fourth minus x to the third plus 4x squared minus 2x minus 4 equals 0. Oh boy. So this is quartic, and I'm probably going to have to use the rational root theorem here. Yep. All right, so let's remember what we do here. First, p must be a factor of my constant, negative 4. So p can be plus or minus 1, plus or minus 2, or plus or minus 4. Now q must be a factor of my leading coefficient, which is 3. So q can be plus or minus 1, or plus or minus 3. Now all of my possible rational roots have to be p over q. So if I took my p's and I put them over plus or minus 1, I just get my p's. Plus or minus 1, plus or minus 2, or plus or minus 4. Now, there are other possible rational roots like plus or minus 2/3, plus or minus 4/3, you know. But again, dot, dot, dot. I usually don't need those, so I just put this here as a little reminder to myself. All right. Now, I usually do like 1 and negative 1 with direct substitution, but you know what? When I'm looking for the roots of a quartic, I might need a quotient polynomial here, so I'm just going to go ahead and do my synthetic substitution now. All right, let's put a 1 in the box, and then let's write down our coefficients of our quartic here. All right, we're going to do a shotgun method. So the quartic coefficient would be a 3. The cubic would be a negative 1. The quadratic would be a 4. The linear would be a negative 2. And the constant would be a negative 4. All right, so shotgun method. Let's bring down the 3. 3 times 1 is 3, minus 1 is 2. 2 times 1 is 2, plus 4 is 6. 6 times 1 is 6, minus 2 is 4. Oh, look at that. And 4 times 1 is 4, minus 4, and I get my first 0. So P of 1 equals 0. Okay, now, I would go on right now and check 1 as a double root, but look at what I have here. 3, 2, 6, 4. Okay, isn't that a cubic with 4 terms? Do you think that grouping might work again? Let's take a peek at this now. Q of x equals, well, this is a cubic now, and I have 3x squareds, or excuse me, 3x to the third plus 2x squared plus 6x plus 4. So I have a quartic with 4 terms. Can I group again? All right, well, let's take the first two. Okay, what's the common factor of 3x to the third plus 2x squared? That would be an x squared. Okay, let's bring that out. And then distributive property, x squared times what is 3x to the third? That'd be a 3x. X squared times what would be 2x squared plus 2. And I'm hoping I have that binomial factor in the other grouping, so I'm just going to put this over here now. 3x plus 2, and then I look, and I have a 3x plus 2, all right? And I need a 6x here, so 3x times what is 6x? That'd be a plus 2. And then make sure it works, so let's double check. 2 times 3x is 6x, and 2 times 2 is 4. It works, so I am almost done. So the common binomial factor is 3x plus 2. Let's put that there. And that's being multiplied by x squared and then positive 2. So there's my two factors right there. And I can't factor any farther, so I better start solving with the zero product property of algebra. So this means that if x squared plus 2 equals 0, then x squared equals negative 2. So x would equal plus or minus the square root of negative 2. Now I need to clean this up. So that's going to equal plus or minus, and you see the factor of negative 1 under the radical. That would come out as an I. And the 2 stays under the radical to get a root 2. So these are two complex conjugates right there. And I have 2 more roots, it looks like. So let's think about this. Okay, my other factor is 3x plus 2. If that was equal to 0, then 3x would equal negative 2, so x would equal negative 2/3. Now I have 3 roots right there, but this is a quartic, so I have a 4th root. Let's not forget, remember our original root of 1? There you go. There it is, and there's my 4 roots. Okay, number 11. Compare and contrast solving polynomial equations by using technology and factoring. Well, technology. Well, we just solved an equation using our calculator. That's our technology, and we did that. When we did that, what did we get? We had 2 approximations. I think we had negative 0.6 and then 1.6. Now, those approximations are great, but if we're an engineer, if we're designing jets or something like that, all right, we need to do things like factoring so we get exact solutions, all right? Anytime we use an approximation as an engineer, we are introducing error into our situation, and that can compromise the integrity of whatever we are designing. Now, my son's a commercial pilot. I am counting on you future engineers to be able to always come up with exact solutions so the integrity of the planes that he is flying in the air will never be compromised. Now, number 12. Find the sum and the product of the roots of 2x to the third minus 5x squared minus x plus 8 equals 0. All right, remember theorem 5? This is simple, all right? Theorem 5, all right? Any polynomial equation, the sum of the roots will always be the opposite of a sub n minus 1 over a sub n. And the product of the roots could be, if n is even, the constant over the leading coefficient, and if n is odd, it's the opposite of the constant over the leading coefficient. So to answer a question like this, all I need would be a sub n minus 1, and a sub 0. So look at this cubic equation. Isn't a sub n my leading coefficient? 2. And isn't a sub n minus 1 then the quadratic coefficient right here, negative 5? And a sub 0 is my constant. What's my constant? It is an 8. So the sum would be, well, the sum is always the opposite of a sub n minus 1 over a sub n. That would be the opposite of negative 5 over 2. The sum is 5 halves. What's the product? Well, the key to the product is this is a cubic polynomial equation. So my n is odd, so I have to use the opposite of a sub 0 over a sub n. So the opposite of my constant is negative 8 over my leading coefficient 2, that'd be a negative 4. That's the sum and the product of the roots of 2x cubed minus 5x squared minus x plus 8 equals 0. Wow. Find number 13. Find a cubic equation with integral coefficients and roots 3i and negative 5. Well, this is a cubic equation, and they have given me 2 roots. But I hope you see 3 roots. So we're going to use roots 1 and 2. Well, one of the given roots is 3i, which is a complex number. And if I have a complex root, I know its conjugate must also be a root. So my first 2 roots are actually plus or minus 3i. And I'm going to use these 2 complex conjugates for my quadratic factor. And then for my third root, I'm going to use the negative 5. And I'll use that for my linear factor. So I'm already almost set up right now. Y equals, well, if I have a root of negative 5, I have a factor of x plus 5. And then for the quadratic, where I'm using my plus or minus 3i, right there, well, any quadratic can be written in the form x squared minus the sum of the roots times x plus the product of the roots. So let's add plus or minus 3i, and then let's multiply them. So 3i plus negative 3i is 0, so I have 0 x's, and then 3i times negative 3i would be negative 9i squared. I squared is negative 1, so that's a positive 9. So the product is 9. I am done right now. I know that y has to equal x plus 5 times the x squared minus the sum of the roots times x plus the product of the roots. Well, I have 0 x's, but I have a product of 9. X squared plus 9. Beautiful problem. Number 14. P of x is a cubic polynomial with real coefficients. Explain why an imaginary number cannot be a double root of the equation P of x equals 0. Okay, well, let's think. A cubic has 3 roots, maximum of 3 roots, I should say. And if one of my roots is an imaginary number, all right, then its conjugate would also be a root. So if I have an imaginary double root, then its conjugate would also be an imaginary double root, giving me 4 roots, and a cubic cannot have 4 roots. So let's write that down officially. If an imaginary is a root, its complex conjugate must also be a root. Therefore, a polynomial with an imaginary double root must be at least 4th degree. That is, the conjugate must also be a double root, giving us 4 roots. A cubic cannot have 4 roots. All right, that's the review for Chapter 2. I hope you enjoyed it. This is some really good stuff. And I just hope you're really enjoying pre-calculus. You all have a great day.